Welcome to this specialized masterclass on scalars and vectors. We will focus on the rigorous mathematical derivation of vector laws and their physical interpretation. By the end of this video, you will master the geometry of force and motion. This flowchart shows our progression. We will define scalars versus vectors, analytically derive vector addition, learn vector resolution into components, and conclude with the dot and cross product derivations. A scalar quantity is fully described by a magnitude and a unit. Scalars like mass and temperature are independent of direction and follow the rules of ordinary algebra for addition. A vector quantity requires magnitude, direction, and must obey vector algebra. It is represented geometrically by an arrow, where the length shows the magnitude and the arrowhead points the direction. A unit vector specifies direction with a magnitude of exactly 1. It is derived by dividing a vector by its own magnitude. This acts as a pure direction tool, fundamental for coordinate math. Our goal is to derive the resultant r of two vectors, a and b, inclined at angle theta. Using the law of cosines, r is the diagonal of the parallelogram formed by a and b. We will now derive this formula analytically. To proceed, we extend vector a and drop a perpendicular from vector b. This decomposes vector b. The base of the larger right triangle is a plus b cosine theta, and the height is b sine theta. We apply the Pythagorean theorem to the large right triangle. The square of the hypotenuse r is equal to the square of the base plus the square of the height. We substitute our geometric values into this theorem. We expand the squared terms using the identity for a plus b squared. This yields a squared plus b squared cosine squared theta plus 2ab cosine theta plus b squared sine squared theta. By factoring out b squared, we use the trigonometric identity. Sine squared theta plus cosine squared theta equals 1. This significantly simplifies the middle portion of our equation. The final analytical formula for the magnitude of the resultant r is the square root of a squared plus b squared plus 2ab cosine theta. This is a critical result in physics. To find the direction, let alpha be the angle between r and a. Using the large right triangle, the tangent of alpha is height over base, which equals b sine theta divided by a plus b cosine theta. When vectors are parallel, the angle theta is 0, and the cosine is 1. The formula simplifies to a plus b, giving the maximum possible resultant magnitude. For anti-parallel vectors, the angle is 180 degrees, and the cosine is -1. The resultant simplifies to the absolute difference of the magnitudes, which is the minimum combined effect. Resolution is the reverse of addition. It is the process of splitting a single vector into two or more mutually perpendicular components, allowing us to analyze complex motions along separate axes. Using trigonometry, the horizontal component a sub x is a times cosine theta, and the vertical component a sub y is a times sine theta. These components fully replace the original vector. In algebraic vector form, vector A is the sum of its components multiplied by the unit vectors I hat and j hat. The magnitude can be verified using the Pythagorean theorem on the components. The scalar or dot product results in a single number. It is the product of the magnitudes of two vectors and the cosine of the angle between them. Physically, it measures how much one vector points along the other. For orthogonal unit vectors, the dot product of a vector with itself is 1, since cosine of 0 is 1. The dot product between perpendicular unit vectors, like I hat and j hat, is 0, since cosine of 90 is 0. To find the dot product algebraically, we multiply the two vector forms. Due to the orthogonality property, the cross terms vanish, simplifying the calculation significantly. The total dot product, vector A dot vector B, is the sum of the products of their corresponding components, a sub x times b sub x, plus a sub y times b sub y. This is a simple algebraic form. The vector or cross product results in a new vector perpendicular to the plane formed by the input vectors. Its magnitude depends on the sign of the angle, and it represents rotational quantities like torque. For unit vectors, the cross product of I hat and j hat yields k hat, defining the third dimension. Crossing a vector with itself is 0, because the sine of 0 degrees is 0. The cross product is derived using a matrix determinant. We set up the matrix with unit vectors, vector A components, and vector B components, then expand the determinant to find the resulting vector. The resulting vector components are differences of cross-multiplied pairs from the determinant expansion. This structure ensures the final vector is perfectly perpendicular to the input vectors. Relative velocity is a vector subtraction problem. We find the relative motion of A as observed by B by resolving each velocity into components and subtracting the observer's motion from the object's motion. For constant acceleration, the position vector r at time t equals the starting position plus the initial velocity vector times time plus 1/2 the acceleration vector times time squared. This governs all trajectories. Velocity in a plane is the first derivative of the position vector. For constant acceleration, the velocity vector equals the initial velocity plus the acceleration vector multiplied by time. To derive projectile paths, we break the initial launch velocity into horizontal and vertical components. We assume horizontal acceleration is 0 and vertical acceleration is -g due to gravity. To find the time of flight, we set the vertical displacement y to 0. Solving for t yields two solutions, t equals 0 at launch and t equals 2u sine theta over g, which is the total time in the air. For maximum height h, the vertical velocity v sub y is 0. Using the third kinematic equation, we derive that h equals u squared sine squared theta divided by 2 grams. Horizontal range r is the horizontal velocity times the total time of flight. By applying the double-angled trigonometric identity, we derive the classic formula for the maximum horizontal distance. To find the path trajectory, we eliminate time t. We solve the horizontal position equation for time and substitute this expression into the vertical position equation, linking height and horizontal distance directly. The final simplified trajectory equation, y equals ax minus bx squared, is the mathematical signature of a parabola. This confirms that all projectiles follow a parabolic arc. In uniform circular motion, speed is constant, but velocity changes constantly because the direction turns. Angular velocity is the linear speed divided by the radius of the circle. Centripetal acceleration is derived from the change in the velocity vector. The geometry shows the acceleration is always directed toward the center, with a magnitude of velocity squared over radius. Lami's theorem applies to 3 forces in equilibrium at a point. It states that each force's magnitude is proportional to the sine of the angle between the other 2 forces, applying the law of sines to forces. We verified the centripetal acceleration formula using dimensional analysis. Both the left side and the right side simplify to length per time squared, confirming that the mathematics are physically consistent. In conclusion, we have developed the full mathematical toolkit for planar motion. These derivations, from algebraic foundations to vector calculus applications, allow us to predict and quantify the physical world with precision.